Hi, my name is Anissa Sofia binti Azman.
Hi, my name is Panela Anna Richard.
Hi, my name is Viziatul Jannah.
Next, for the objective of this case study is to investigate the behavior of electric charge and electric field, the interactions and the application in real-world scenario.
The definition of static electricity is an imbalance between negative and positive charge in an object. These charges will build up on a surface of an object until it is released or discharges. There are three types of charges, which is electron as negative, proton as positive, and neutral as neutron. For the conversion is total electric charge in an insulated system will remain constant. Insulator is the material that do not allow electricity to pass through them, while conductor is material that allow the flow of electric current through it. This is the 5 example of conductor and insulator. The 5 example of conductor is silver, gold, copper, steel, and seawater, while the example for insulator is rubber, glass, oil, diamond, and dry wood. There are three types of indirect charge. First one is charging by conducting. It's a process involves touching of a charged particle to a conductive material. The second one is charging by induction. It's a process where the charged particle is held near an uncharged conductive material that is grounded on a neutrally charged material. The last one is charged by friction. It's a process involving rubbing one particle on another. For example, when we rub balloon on our hair, the balloon will become negatively charged. This is due to transfer of electron from our hair to the balloon, and the balloon become negative while our hair become positive charged. Coulomb's law states that the electric force between charges Q1 and Q2 is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. So this is the formula of Coulomb's law. F is equal to K Q1 Q2 over R square, where F is force in Newton, K is Coulomb's constant, Q1 and Q2 is charges of mass 1 and 2 in coulombs, and R square is distance between the charges in meter. So this is the interaction between two charges particles, where positive and positive or negative and negative attract to each other. It will produce repulsive force. Meanwhile, where positive and negative charges attract to each other, it will produce attractive force. And these are the Coulomb's law example.
Okay, for the next is electric field, or it's known as E. An electric field is an region around a charged particle or object in which another charged particle experiences a force. It is a vector field that represents the influence of electric charge on the surroundings. The strength and direction of this electric field at a point are defined as the force per unit positive charge placed at that point. Mathematically, it is expressed as a E equal to F over Q, or E equal to K Q over R square. E is electric field. SI unit is as a volt per meter. For the F, it force experienced by the charge, and SI unit is for Newton. For Q, it was a magnitude of the test charge. SI unit is coulomb or C. For electric field or E pattern, the electric field pattern is a visual representation of how an electric field behaves around charge or a system of charge. It is depicted using electric field lines that show the directions and strength of the electric field. As we can see here, there are two types of a charge, which is positive and negative charge. For the first one is positive charge. Um, Field line radiate outward symmetrically from the charge. The directions of positive charge is it indicated that a positive test charge would be repelled. As for the negative charge, field line converge inward symmetrically toward the charge. The directions of this charge shows that a positive test charge would be attracted. For the two like charge, positive positive or negative negative, it will be repel each other because from both charge and a field line will start from both charge and bend away from each other. And they will never crossing because this indicated repulsion between the charge, and in the region between the charge, field line curve outward showing a weaker field. And then we continue to the electric field in daily life. Electric fields are present in many aspects of daily life, even if they are not always direct, noticeable. For first example that we have shown here is lightning. Lightning occurs due to the electric field between clouds and the ground. The separation of charge in the cloud creates a strong electric field, which eventually leads to a discharge in the form of lightning bolt. And then for the devices, um, every day we as a modern lifestyle, we use devices as our daily life. Example like we charging our phone or other devices involve electric field within the chargers and batteries. Also facilitating the flow of charge to store energy. That's why devices is as one of our electric field in uses of daily life. And for the last example that we have shown here is electrophoresis. Electrophoresis is had uses in medical and scientific laboratories. Electrophoresis employs an electric field to separate molecules like DNA or protein based on their charge and size. So electrophoresis is more to in medical field. And then we continue to the field lines. Field lines, also called line of force. It was a visual representation used to illustrate the direction and strength of a field, such as an electric field or magnetic field in space. They provide a way to conceptualize how a field interacts with charged particles of magnetic materials. For the direction of the field lines, as we can see here in this slide, is field line indicates the direction of force experienced by a positive test charge placed in the field. For electric field line points away from the positive charge. Uh, for the field line point toward negative charge also have indicated in this picture because field line never intersect because the field at a point has a unique direction, and then they originate from positive charge and terminate on negative charge. In the case of uniform field, the field lines are parallel and equally spaced. Example like if a point charge, field line radiate outward for a positive charge or inward for a negative charge as a symmetrically. And then field line emerge from the positive charge and curve toward the negative charge. It's showing the interaction between the two. For the parallel plates, in a uniform electric field between two parallel plates, the lines are straight, parallel, and equally spaced. And then as for the solution of electric field, we have put one of example how to solve the question or the problem. Here we can see here there are two types of charge, which is both of it positive. And then we got the electric field, we got the Q, and then the distance. Here, we use the E equal to KQ over R square. As we can see, K is indicates to 9 times 10 power of 9. And then it's times to the Q1, which is Q1 is indicates to 2.550 microcoulomb. As we can see here, 2.50 times to the 1 times 10 to the power of negative 6. 1 times 10 to the power of negative 6 is indicates to the microcoulomb change to the coulomb. That was a formula. If our questions was given based on the microcoulomb. And then it's over to 0.20 square. Why I don't use 20.0 centimeter? Because if we want to solve the question, we need to change it. So centimeter is changed to meter, and then we solve it, calculate it, and then we can get 562,500, and we need to round it off to the 56300 Newton coulomb, but to the power of negative 1. And then as as we solved before, it was a first electric, and then we need to solve the second one, which is the Q2. Okay, as we can see here, the Q2 is towards to the left. So we solve it like a Q1 using the same formula, and then we can get the answer is as 94921.875, and then round it off to 94900 Newton coulomb to the power of negative 1. Here, I want to push about the positive and negative charge. Why both of it have a same charge, but after the solve, we got the two different charge. As we can see here, E1 equal to positive 56300 I, which is indicates to the way, to the directions, which is symmetrically. Newton coulomb to the power of negative 1. And then for the E2 is equal to negative 94900 I Newton coulomb to the power of negative 1. Why here? Because Q2 is moved towards the left. Then Q1 is follow the way, which is, that's why it's stay as a positive charge. And then we need to total up it, sum up it, E1 plus E2, and we can solve it, get the answer 468,100 I Newton coulomb per to power of negative 1, and that's it.
electric flux is defined to be the depth of the product of the electric field and surface area vector. It is a scalar quantity. So here we can see a formula. So for E is electric field and S for area of the surface, E for area negative. And for the angle between this electric field and lines and the normal perpendicular to S, and also the flux electric field through a closed symmetrical surface. You can see the picture in this slide. Gauss' law is the electric flux across any closed surface is proportional to the net electric charge here enclosed by the surface. Here is a formula for electric flux through a closed surface enclosing an equilibrium, and here is total charge equals within V, and EO is electric constant, which is 8.854 times 10 power of negative 12. So here you can see we have two example for Gauss' law and electric flux. So you can hear in this slide. For conclusion, electric charge are responsible for creating electric field that govern the interaction between charged particles. And then understanding electric charge and field provides a foundation for exploring more complex phenomena in physics and engineering.